We're going to do a little bit of a review on differentiation from year 11. So, differentiation, derivatives of a function. So remember, average rate of change is your rise over run. The gradient at a point would then be when you take the limit of it and put it on the point, which means if you have a polynomial, then if f of x is equal to a x to the power of n, then f dash of x is where you take the power down, that's why it's na. Then you have x to the power of n minus 1, so you subtract the power by 1. Okay, to differentiate f of x equals to that, take the power down, subtract the power by 1. This one, because you have 1 over x, I would rewrite that in terms of a negative power, like so. So then that becomes negative 1, sorry, not negative 2, times a half, then subtract the power by 1, so it's 2. Put all of that together. Now, normally you can stop here if you like. I'm going to change power back so that it has a positive index. You don't have to. You should only do it if you're required, but that's how you would do it. The second one, see how you have two separate terms? You need to separate two terms. And also you need to show that this doesn't work for x equals 0 because of the denominator. Anyway, separate it into two separate fractions, like so. Simplify whatever you need to. Remember, square root of x is x to the power of a half. There's a 2 on the bottom, so it's minus 2. So then we get, so we're going to rewrite the power now. A half minus 2 is negative 3 over 2. I'll put the quarter in the front so you don't forget that it's a separate number. Now we can take the derivative. That's a quarter times negative 3 over 2. And then the other one is, you subtract it by 1, so you get negative 5 over 2. And because it's x to the power of 1, when you subtract the power, you get x to the power of 0, which is actually just a 1, so that just becomes 3/4. So that's negative 3 over 8, x to the power of negative 5 over 2, minus 3/4, or if you like, if you want to rewrite it, that's negative 3 over 8 square root, because there's a 2 on the bottom of a fraction, x to the power of 5, all on the denominator of that fraction. Now, just a quick notation thing. You might notice that the derivative is x, and just remember if it's y, then the derivative is dy dx. Okay, if f of x is equal to x minus x squared, what is the gradient of the curve when x is equal to negative 3? Simply find the derivative. Then sub it in at negative 2. Expand it out. And then simplify it. 4, 64, so 61. Okay, B. If f of x is equal to 2 square root of x minus 4, determine the coordinates of a point where the gradient is 2. So, simply find the derivative again. Oh, 4 goes away. Then we're going to find where the gradient is equal to 2. So f dash of x is equal to 2, but remember f dash of x is 1 over square root of x. That means we can solve for x. Then, because x is equal to a quarter, we solve it back into f of x. Then we write down the coordinates together. Alright, so turning points are where the gradient is equal to 0. And then if we're looking at the gradient graph, the gradient where it's positive, the f dash of x graph will be above the x-axis. Where it's negative, it's going to be below. Now, best way to do this, instead of graphing it over the same set of axes, I know that's what it says on the example, is to actually graph it underneath. The reason for that is, if you graph it underneath and you put a ruler down, wherever you see a turning point, you can match it and put on the graph underneath like so. So these two particular points, gradient is going to be 0. Then, if you have a look to the left of the first turning point, which is at negative 0.2, to the left of it, you have a decreasing graph, so it's going to be below the x-axis. Then it's increasing in between the two turning points. Whoops, what am I doing? Like so. So it's increasing and then going back to 0, otherwise it can't, then it's decreasing. Alright, part B, state the domain of a gradient function f dash of x for the function shown. I probably should have given myself more space than that, but anyway. Now, for the gradient function, you can't have any sharp points, and you can't have any discontinuities, so that there is not connected, and that here is a sharp point, which means we simply write down all of the domain except for those points. The domain is all real, except the point at 1, and then the point at 4. If you like, the other notation is negative infinity up to 1, and we're not including 1, so make sure you use circular brackets, and then up to 4, and then 4 to infinity. Alright, last little section. The gradient of any straight line is tan theta. The gradient of parallel lines have the same gradient. And then perpendicular lines, we have the two multiplying to give you a negative 1. Horizontal tangent is 0, and then vertical tangent is undefined. Alright, so consider a function f of x equals to 1 minus x, x minus 3, x minus 6, all multiplied together. And then A, find the gradient of a tangent to the curve at the point 4, 6. So firstly, we need to find the derivative. To do that, simply multiply it out. We have 1 minus x times x squared minus 9x plus 18. Then expand it out, we have x squared minus x cubed minus 9x plus 9x squared plus 18 minus 18x. Then put all of the same terms together. Then find the derivative. And sub in 4. That gives us a 5. Then put it in our linear equation, which is y minus y1 equals to m x minus x1. So then we have y minus 6, and our gradient is 5, and x minus 4. So then we get 5x, what's that, minus 20 plus 6, so minus 14. Now, if you want the equation of a line perpendicular, we then need to find the perpendicular gradient, which is negative 1 over the other. Then sub it back in again. And then simplify.